NENOMATICA, where mathematics meets YouTube excellence. In this lesson, we will solve a quadratic inequality using a clean, step-by-step sign table approach. Our problem is the fraction 6 minus x squared over x is greater than 1. We will transform it, find critical points, build a sign chart, and read the solution. Step 1. Move everything to one side and combine into a single fraction. Subtract 1 from both sides, then combine using a common denominator x. Finally, multiply the numerator by -1 to make the leading term positive, remembering to reverse the inequality. Step 2. Find the roots of the numerator. Set x squared plus x minus 6 equal to 0 and factor. That gives x plus 3 times x minus 2 equals 0. So the numerator zeros are x equals -3 and x equals 2. Step 3. Find the root of the denominator. The denominator x equals 0 is an undefined point for our expression, so x equals 0 must be excluded. Step 4. Build the sign chart. Our critical points are -3, 0, and 2. We draw 3 rows, the numerator sign, the denominator sign, and their quotient p of x. The numerator is positive to the left of -3 and to the right of 2, and negative in between, with zeros at -3 and 2. The denominator x is negative left of 0 and positive right of 0, with 0 at 0 indicating undefined for the full expression. Combining signs gives p of x negative on negative infinity to -3, and on 0 to 2, positive on -3 to 0, and on 2 to infinity. Step 5. Our inequality is strictly less than 0. From the p of x row, the negative intervals are x less than -3, and 0 less than x less than 2. Remember that x equals 0 is excluded because the expression is undefined there. So the solution set is all real x with x less than -3, or between 0 and 2. In this lesson, we will solve a quadratic inequality in one variable using a clean, reliable sign analysis. The problem is the fraction x plus 1 over x minus x over x minus 1 is less than or equal to 2. Step 1. Move everything to the left side, so the inequality is less than or equal to 0. Subtract 2 from both sides. Step 2. Find a common denominator and combine. The common denominator is x times x minus 1. Combine the numerators over this denominator. Now expand the numerator and simplify. Step 3. Analyze the numerator. Here a equals -2, b equals 2, and c equals -1. The discriminant is b squared minus 4ac, which equals 4 minus 8, that is -4. Since the discriminant is negative and is negative, the numerator is always negative for all real x. Step 4. Analyze the denominator. Set x times x minus 1 equal to 0. We get x equals 0 or x equals 1. These values make the expression undefined, so they are excluded from the solution. Step 5. Build a sign table using the critical points 0 and 1. Draw a number line and mark open circles at 0 and at 1. The numerator is always negative, so mark minus signs in every interval. For x less than 0, the denominator x times x minus 1 is positive. For x between 0 and 1, the denominator is negative. For x greater than 1, the denominator is positive again. Therefore, the fraction is negative on the left and on the right, and positive in the middle. Step 6. Read the solution from the sign table. The fraction is less than or equal to 0 on the intervals -infinity to 0 and 1 to positive infinity. Recall that 0 and 1 are excluded because the expression is undefined there. Therefore, the solution set is all real x less than 0 or greater than 1. In this lesson, we will solve a rational quadratic inequality step by step using a clean sign analysis and a clear number line visualization. Step 1. Move all terms to one side and compare to 0. We subtract 1 over x squared plus 1 from both sides. Step 2. Combine the fractions over a common denominator. That denominator is the product of 2x squared plus x plus 1 and x squared plus 1. Now distribute the negative sign in the numerator and combine like terms. The numerator simplifies to -x squared minus x. So the inequality becomes the fraction with -x squared minus x on top, over the same always positive denominator, greater than or equal to 0. Step 3. Find the roots of the numerator because the denominator has no real roots, as we will show, so it will not change the sign. Set negative x squared minus x equal to 0. That factors as negative x times x plus 1 equals 0. So the critical points are x equals negative 1 and x equals 0. Step 4. Check the denominator factors for real roots. First, x squared plus 1 equals 0 has discriminate 0 squared minus 4 times 1, which is negative 4. No real roots, and since the leading coefficient is positive 1, this factor is always positive. Second, 2x squared plus x plus 1 equals 0 has discriminate 1 squared minus 4 times 2 times 1, which is negative 7. Again, no real roots, and with leading coefficient 2, this factor is always positive. Therefore, the denominator is always positive for all real x. Step 5. Perform the sign analysis. Since the denominator is always positive, the sign of the entire fraction matches the sign of the numerator negative x squared minus x, or negative x times x plus 1. We test intervals around the critical points at negative 1 and 0. To the left of negative 1, the expression is negative. Between negative 1 and 0, it is positive. To the right of 0, it is negative again. Because our inequality is greater than or equal to 0, we take the interval from negative 1 to 0, including the endpoints. Therefore, the solution set is the closed interval from negative 1 to 0. We include both endpoints because the inequality allows equality and the denominator is never 0. In this video, we will verify whether given values satisfy two quadratic inequalities by direct substitution and simplification. Let's begin with a quick example setup, and then apply the substitution rule carefully. Here are the two checks we will perform. First, 6z minus z squared is greater than or equal to z squared plus 3, with z equals 4. Second, open parenthesis x plus 1 close parenthesis squared is strictly greater than 3x plus 1, with x equals 1. We will use a simple rule. If a value satisfies an inequality, then substituting that value should produce a true numerical statement. Part A. We substitute z equals 4 into the inequality 6z minus z squared is greater than or equal to z squared plus 3. That gives 6 times 4 minus 4 squared on the left and 4 squared plus 3 on the right. Simplify each side. 24 minus 16 is 8, and 16 plus 3 is 19. We now compare 8 and 19. Since 8 is not greater than or equal to 19, the inequality is false for z equals 4. Quick challenge. If we tried z equals 1 instead, would the inequality be true or false? We will return to that in the summary. Part B. Now we test x equals 1 in the inequality. Open parenthesis x plus 1 close parenthesis squared is strictly greater than 3x plus 1. Substitute to get open parenthesis 1 plus 1 close parenthesis squared on the left, and 3 times 1 plus 1 on the right. Simplify both sides. 2 squared is 4, and 3 plus 1 is 4. We now compare 4 and 4 under a strict greater than. Since 4 is not strictly greater than 4, the inequality is false for x equals 1. In this lesson, we will prove the inequality at times the quantity a plus b times the quantity b plus 1 is greater than or equal to negative 1/3. We will present two visual intuitive methods using the discriminate and completing the square. First, expand the left side and move the constant to the left side. That gives a squared plus ab plus b squared plus b is greater than or equal to negative 1/3. Adding 1/3 to both sides, we rewrite as a squared plus a b plus b squared plus b plus 1/3 is greater than or equal to 0. We will call this entire expression S. Our goal is to show S is always non-negative. Method 1. Use the discriminate. Treat S as a quadratic in A. Here the coefficient of a squared is 1, the coefficient of it is b, and the constant term is b squared plus b plus 1/3. The discriminate is b squared minus 4ac. Now simplify the discriminate step by step. We get b squared minus 4b squared, minus 4b minus 4/3. Combine like terms for b squared to get negative 3b squared. Factor out negative 3. Complete the square inside. That becomes negative 3 times b plus 2/3 quantity squared. Because a square is always non-negative, the discriminant is less than or equal to 0. Intuition. With leading coefficient positive, the graph of the quadratic is an upward opening parabola. If the discriminant is not positive, the parabola never crosses the horizontal axis, so the quadratic is always non-negative. Therefore, with delta less than or equal to 0 and a positive leading coefficient, the quadratic is always non-negative. Hence, S is non-negative for all real A and B by method 1. Method 2, completing the square. We start from S equals a squared plus A, B plus B squared plus B plus 1/3. Multiply by 4 to clear fractions. 4S equals 4 squared plus 4, AB plus 4B squared plus 4B plus 4/3. Now split the 4b squared term as b squared plus 3b squared to complete squares in two groups. Group 1 is 4 squared plus 4ab plus b squared. Group 2 is 3b squared plus 4b plus 4/3. The first group is the square of 2a plus b. For the second group, factor out 3. That yields 3 times b squared plus 4/3 b plus 4/9. Recognize a perfect square, b plus 2/3 quantity squared. Put it together. 4 south equals the square of 2a plus b, plus 3 times the square of b plus 2/3. Each square is non-negative, so the sum is non-negative. Therefore, 4s is at least 0, which implies s is at least 0. To build intuition, think of each square term as an area that can never be negative. We will show two colored squares labeled 2a plus b and square root of 3 times b plus 2/3. Their total area is always non-negative, mirroring the algebra. Since s is at least 0, a squared plus ab plus b squared plus b is at least negative 1/3. Returning to the original form, we have a times a plus b times b plus 1 is greater than or equal to negative 1/3 for all real a and b. Example, we will find the range of m such that the point A of alpha, beta, where alpha and beta are the roots of x squared plus 3x minus 4m plus 8 equals 0, lands in the first or the third quadrant. First, visualize the quadrants. A point is in quadrant 1 or quadrant 3 if its x and y have the same sign, which means their product is positive. We'll shade quadrant 1 and quadrant 3 to keep that idea in mind. The condition for quadrant 1 or quadrant 3 is x times y greater than 0. For our point A of alpha, beta, that means alpha times beta greater than 0. For a quadratic ax squared plus bx plus c equals 0, the product alpha beta equals c over a. For our equation, a equals 1, b equals 3, c equals negative 4m plus 8. So alpha beta greater than 0 becomes c over a greater than 0, which is negative 4m plus 8 greater than 0. Solving gives m less than 2. Next, alpha and beta must be real numbers. That means the discriminant is non-negative. Delta greater than or equal to 0 is b squared minus 4ac greater than or equal to 0. Substituting a equals 1, b equals 3, c equals negative 4m plus 8, we get 9 minus 4 times 1 times the quantity negative 4m plus 8 greater than or equal to 0. That simplifies to 9 plus 16m minus 32 greater than or equal to 0, or 16m minus 23 greater than or equal to 0. Therefore, m is greater than or equal to 23 over 16. Now combine both conditions, m greater than or equal to 23 over 16, and m less than 2 on the number line. We shade from 23 over 16, including the endpoint, up to 2, but not including 2. This intersection is the final solution. To recap, alpha beta greater than 0 puts the point in quadrant 1 or 3, and delta greater than or equal to 0 guarantees real roots. Together, they yield 23 over 16, less than or equal to m less than 2. Final answer. M in the interval from 23 over 16 inclusive to 2 exclusive. Example. In this video, we will solve the inequality 2n squared minus 27n plus 25 less than 0 and count how many natural number solutions it has. Our plan is 3 steps. Step 1, find the roots. Step 2, determine the sign interval where the expression is negative. Step 3, list the natural numbers inside that interval and count them. Step 1, find the roots of the quadratic equation 2n squared minus 27 n plus 25 equals 0. Quick check trick. If a plus b plus c equals 0, then n equals 1 is a root. Here, a equals 2, b equals negative 27, c equals 25, and 2 plus negative 27 plus 25 equals 0. So one root is n1 equals 1. Next, for a quadratic, the product of the roots is c over a. That gives n 1 times n2 equals 25 over 2. Since n1 equals 1, n2 equals 25 over 2. Step 2. Determine where the expression is negative. Since it equals 2 is positive, the parabola opens upward, so the quadratic is negative only between the roots. We place the roots 1 and 12.5 on a number line, mark open circles at those points for a strict inequality, and label the sign regions. Therefore, the solution set to 2n squared minus 27n plus 25 less than 0 is the open interval from 1 to 12.5. Step 3. We now list the natural numbers strictly between 1 and 12.5. Those are 2 through 12 inclusive. We can count them quickly. From 2 up to 12 is 11 numbers. So the inequality has 11 natural number solutions. Recap. In this lesson, we will find all real values of a such that the inequality open parenthesis ax squared plus 2x plus a minus 2 close parenthesis over open parenthesis 2x squared plus 3x plus 2 close parenthesis is strictly greater than 0, holds for every real x. We'll proceed step by step. First, we'll study the denominator. Step 1. Analyze the denominator. Let p1 equal 2x squared plus 3x plus 2. We compute its discriminant, delta equals b squared minus 4ac. That is 3 squared minus 4 times 2, which equals 9 minus 16, which is negative 7. Since the discriminant is negative and the leading coefficient a equals 2 is positive, the quadratic p1 is always positive for all real x. This means the denominator never changes sign and is strictly positive. Step 2. Because the denominator is always positive, the entire fraction will be strictly greater than 0 for all x if and only if the numerator is strictly positive for all x. Let p2 equal ax squared plus 2x plus a minus 2. A quadratic is strictly positive for all real x if and only if its leading coefficient is positive and its discriminant is negative. So we require a greater than 0 and delta sub 2 less than 0. Compute delta sub 2. It equals 2 squared minus 4 times a times open parenthesis a minus 2 close parenthesis. That simplifies to negative 4 a squared plus 8 a plus 4. We need negative 4 a squared plus 8 a plus 4 less than 0. Step 3. Let's solve the inequality in A. Divide both sides by negative 4, which reverses the inequality sign. We get a squared minus 2 or minus 1 greater than 0. Now solve the equality a squared minus 2 or minus 1 equals 0 to find the critical points. The discriminant is 2 squared minus 4 times 1 times negative 1, which is 8. So the roots are 1 plus or minus square root of 2. Because the quadratic opens upward, the inequality greater than 0 holds for a less than 1 minus square root of 2 or for a greater than 1 plus square root of 2. That is, an open parenthesis, 1 plus square root of 2 comma infinity close parenthesis. Recap. The denominator 2x squared plus 3x plus 2 is always positive because its discriminant is negative and the leading coefficient is positive. Therefore, the numerator must be always positive. That requires a greater than 0 and the discriminant of ax squared plus 2x plus a minus 2 to be negative. Solving the resulting inequality yields a less than 1 minus square root of 2 or a greater than 1 plus square root of 2. Intersecting with a greater than 0 leaves only a greater than 1 plus square root of 2. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.